Welcome to Mathematics. Today we'll be learning about Edexcel Chemistry Unit 5 Transition Metals. So before we begin learning about transition metals, we have to learn what D block elements are. So if we have our periodic table over here, so this section over here, so between group 2 and group 2 and 3, this part contains the D block elements. All transition metals are D block elements. However, it's not the other way around. So this is what we have to remember, that all transition metals are D block elements, but it's not the other way around. All D block elements are not transition metals. Now, if you want to know why they are called D block elements, it's because in this case, so for elements in this region, their last or the highest energy electron feels d subshell. So if I look here, these are the S block elements, these are the P block elements, and in between that we have the D block elements. So for a P block element like boron, its electronic configuration is 1s2, 2s2, 2p1. So the last electron goes to fill the p subshell. So that's why it's a p block element. For scandium, its electronic configuration is, if we write using argon, we have argon and then 3 more. So 4s2, 3d1. So the final electron goes to fill the d subshell. So scandium is a d block element. And transition metals are D block elements which have one stable atom with an incompletely filled d orbital or d subshell. So I'll explain what I mean by that. So it is a D block element with at least one stable ion with a partially filled subshell or partially filled d subshell. So it's not a partial. A d subshell has 5 orbitals. 1, 2, 3, 4. So this is a d subshell. So this is a fully filled d subshell. If I remove some electrons from it, so this is an incompletely filled d subshell since we are not using it to its full capacity. A d subshell can store 10 electrons, so we are only storing 9 over here. So this is incompletely filled. This is also incompletely filled. We are only using 8. We are only using 7, 6, 5. So it's still incompletely filled. We can go on until there's 1. However, if we have 0, this is not partially filled. This is a completely empty d subshell. So this won't work. So we need so for a d block element to be a transition metal, it must have a stable ion. So an ion that forms in nature, or we can form and it stays as it is without immediately reacting, and it has 1 to 9 electrons in the or d orbital or d subshell, not orbital, then it can be a transition metal. So a d block metal which isn't a transition metal is scandium. So scandium has an electronic configuration of argon 3d1 4s2. Now the only stable ion of scandium is scandium 3+. This has an electronic configuration of argon 3d0 4s0. So this has no electrons in the d subshell. Since this is the only stable ion of scandium, it is not a transition metal. From that we can conclude that scandium is not a transition metal element. So this is for an empty 3D subshell. There is another D block element which isn't a transition metal, and that is zinc. So zinc has a atomic number of 30. Its electronic configuration is argon 4s2 3d10. Now the only stable ion for zinc is zinc 2 plus. This atomic number is still gonna be 30, but there are gonna be 2 electrons less than 30, so we'll have 28 electrons. For argon, this is 4s0 3d10. Now you might have a question on why the electrons are being lost from 4s instead of being lost from 3d. So although 3d is a higher energy subshell, 4s is the outermost subshell. So 4s is on the fourth shell. It's on the fourth quantum shell, while 3d is in the third quantum shell. So when we remove an electron, the electron is removed from the 4s subshell since it's the outermost subshell. Since it's the outermost electron shell, even though it's not the highest energy electron shell. So in this case, the opposite happens. We have a full 3D. We have a full D subshell. Therefore, zinc is not a transition metal element. You can also note down that the 4s electrons are lost before the 3d electron. So this is the reason that it's lost from the 4s subshell instead of the 3d subshells, because if the 4s electrons are lost, the ion becomes smaller than if the 3d electrons are lost. So this makes it more energetically favorable, as having a smaller ion makes the lattice energy and hydration enthalpy more exothermic. Now we have learned 2 exceptions or 2 D block elements which are not transition metals, which are zinc and scandium. So scandium and zinc are not transition metals. However, titanium, vanadium, chromium, manganese, iron, cobalt, nickel and copper are, and in between them we'll mainly study about vanadium, chromium, manganese, iron, cobalt, nickel and copper. So these are the ones we'll mainly study about. So for example, iron has an atomic number of 26. It has an atomic configuration of argon 4s2 3d6. There are 2 stable ions of iron. One is iron 2 plus. In this case, we'll lose the 2 electrons from the 4s subshell. So it will become 4s0 3d6. So we have 6 electrons in the 3d subshell. So this is a partially filled orbital. So partially filled d orbital. Therefore it's a transition metal. Now we'll be learning about some properties of transition metals. The first property is that it forms colored compounds and ions. So most group 1 and group 2 ions and compounds are mainly white or gray. However, for transition metals we can have colorful stuff. For example, gold itself is a transition metal and it's gold in color, and ions of gold are yellow or red in color. You don't have to know information about gold for this syllabus, but we'll have to learn other colors for chromium, manganese, iron, vanadium, cobalt, nickel, copper. So we have to know the colors of their compound in our syllabus. Another property is that it forms ions with different oxidation numbers. So for iron, in this case, we have two different stable ions of iron, iron 2 and iron 3. So this has a configuration of 4s0 3d5. The other transition metals are like this. This allows them to have different oxidation numbers. So this is another property. This property is very important and we'll learn about it more, and we'll have a lot of questions related to this, so we have to remember. Another property it has is that it has high boiling and melting points. So high boiling slash or and melting temperatures. Another property is that it can form complex ions. Can form complex ions or compound. We'll be learning about complex ions shortly. Another property is that it can act as catalyst. They are good catalysts because of the second point, since they can form ions with different oxidation numbers. So it can oxidize and reduce between their forms, so they are very good oxidizing or reducing agents, and hence they are real good catalysts. Now moving off of this point, so the fact of the oxidation numbers, we have a table for the oxidation numbers. So the oxidation numbers that exist for the transition metals, we can also learn it for the other two D block elements we have learned, which are not transition metals. So starting from scandium, then titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Scandium can exist in +2 or +3. The +2 ion is not stable, so I'll highlight the stable ones. Titanium exists in +2, +3 and +4. The +4 is the only stable one. Vanadium exists in plus 1 plus 2 plus 3 plus 4 and plus 5. Only plus 3 plus 4 and plus 5 are stable. Chromium exists in plus 1 plus 2 plus 3 plus 4 plus 5 and plus 6. The stable ones are plus 2 plus 3 and plus 6. Manganese can exist in plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 and plus 7. Of them, 2 and 7 are stable. Manganese 4 is also quite stable. Iron can exist in plus 1 plus 2 plus 3 plus 4. It cannot exist as plus 5. It can again exist as plus 6. From them, 2, 3 and 6 are stable. Then coming on for cobalt, we have plus 1 plus 2 plus 3 plus 4. Plus 2 and plus 3 are stable. For nickel, it's plus 1 plus 2 plus 3 and plus 4, of which only plus 2 is stable. For copper, plus 1 plus 2 and plus 3, only plus 2 is stable. And for zinc, we only have plus 2, which is stable. Copper 1 is stable as well. So this is the table of the possible oxidation numbers of group D elements. Now, for the reason behind this variable oxidation states, we need to learn about the successive ionization energies of transition metals. So we'll briefly move on to that before coming back to this. So for the successive ionization of D block elements, we have to learn about the big jumps. So for scandium, I'll write down the electronic configuration for all transition metals up to zinc. In this case, I'll write it in the form 3d then 4s, since we are removing the electron from the 4s and we are more concerned about the 3d subshell. Now we have to find the first big jump between the successive ionization energies. First big jump. From what we learned previously, we apply that when we move down a quantum shell, so when we move from the fourth quantum shell to the third or the third to second, there is the first big jump. However, the case is different for D block elements, since the energy level of 3D and 4s are almost the same. So energy level of 3D electrons and 4s electrons are almost the same. So when we move from the 4s subshell to the 3D subshell, there isn't that big of a jump. So for scandium, the first jump, instead of being between the second and third, is actually between the third and fourth. And for titanium, it's between the fourth and fifth, and this will go on. So fifth and sixth for vanadium, sixth and seventh for chromium, and so on. And this trend goes on until the 12th and 13th for zinc. And we'll write down why this is the case and why it's not what we have learned before with a big jump when we are changing quantum shells. The reason is the 3d and 4s electrons being very close. in terms of energy levels. And so the first big jump happens after all the 3D electrons are removed. So the third big jump happens 3D electrons have been removed. So this is what happens. Now we'll return to this. The variable oxidation states of the d block elements are due to this fact that the successive ionization energy is steadily changing until the big jump when all the 3D electrons are removed. So the jumps are small over here. So when we go from chromium 2 to chromium 3, the ionic bonding becomes stronger, and this can compensate for the third ionization energy of chromium, which allows it to have different oxidation numbers. In case of transition metals, we can call that the oxidation number or oxidation state interchangeably, and the successive ionization energy increases slowly for d block elements. This ionization energy is provided for by the stronger ionic bonding. The same is in the case of going from iron 2 to iron 3. And now if we observe this table, we can see a trend. So from scandium to manganese, we were having an upward trend. So the oxidation number or oxidation state of the stable ion with the highest oxidation state was increasing from 3 over here to plus 7 over here, and then after that it begins going back down. So this increasing is explained by the fact that more 3D electrons are being involved in the bond. So if we go from scandium, which has only one d subshell electron, while manganese has 5 of them. And this trend, so the oxidation state decreasing, this is explained by iron, cobalt, nickel, copper, zinc having higher and higher nuclear charge. So the electrons are more attracted to their nucleus, which makes it harder for and less likely to be involved in bonding with other molecules and forming compounds. So higher oxidation numbers become less common as we go to the right. So more 3D and 4s electrons are being involved in the bonding when we go from scandium to manganese, which causes the rise in the oxidation number. And after that, the increasing nuclear charge becomes a more dominating factor, causing the oxidation number to decrease since the electrons are more attracted to its nucleus. Now from here, we'll move on to complex ions and compounds. The special thing about complex ions is that it forms dative covalent bonds. So a transition metal is in the middle, and lone pairs from other molecules such as hydroxide or water comes and fills a empty 3d orbital of copper and forms a dative covalent bond with it. So a common complex compound is a CuH2O6. So copper connected with 6 molecules of water. All of them are dative covalent bonds. So something like that. So the definition of a complex ion or compound is that in which molecules or ions form dative covalent bonds with the central metal ion. The molecules or ions that are joined together with the central metal cation are also called ligands, and they form dative covalent bonds. So this is what a complex is. A complex can be either positively charged, negatively charged, or neutral. Now we need to know what ligands are. Ligands are the ions, so it's an ion or compound or a molecule which forms a dative covalent bond with the central metal ion. A ligand cannot be positively charged, it can only be negatively charged or neutral. So we have to remember this specifically. You won't have questions directly about this, but you'll see that ligands cannot be positively charged ever. Now we'll learn about 3 types of ligands. One is a monodentate ligand, so a ligand which can only form one dative covalent bond with the central metal ion. Bidentate ligands are those ligands which can form 2 dative covalent bonds with the central metal atom or ion, and a hexadentate ligand can form 6 dative covalent bonds. So monodentate ligand. Some examples of monodentate ligand would be water, where the oxygen only can form dative bonds. Ammonia also has a lone pair on the nitrogen. We can have OH minus ions, halide ions, so Cl minus, Br minus, I minus. We can also have Cn minus, stuff like that. An example of a complex ion with monodentate ligands would be the example we just saw before. So 6 waters connected to 1 copper. And this will have a charge of +2. You can write H2 or OH2 in any order, doesn't matter. Now for bidentate ligands, so in this case, instead of 1, 2 atoms form dative covalent bonds. Some examples of bidentate ligands would be ethanediate ion, so this ion over here. The oxygens have a lone pair each. This is called an ethanediate ion. Another example would be 1,2-diaminoethan, so H2N, CH2, CH2, NH2. You could write this as an H2 as well, it doesn't matter. The nitrogens have a lone pair on them, so they can form two dative covalent bonds, one with this nitrogen, one with the other one. It's called 1,2 diamino ethane. Now for hexadentate ligands, instead of 1 or 2, we have 6 atoms which can form dative covalent bonds with the central metal ion. The only thing we need to form dative covalent bonds are lone pairs. So we need 6 lone pairs. Hexadentate ligand we'll learn about is ethylene diamine tetraacetate. It's basically a combination of the ethane diet ion and the 1,2 diaminoethane. So we have N CH2 CH2N, and on the nitrogen we have CH2 C double bond O minus 2 on each nitrogen. So we have a lone pair on this oxygen, so 4 of them in total, and we have lone pairs on the nitrogens, so we have 6 lone pairs which can form dative covalent bonds with the central metal ion. Now there is another concept we need to learn about, which is the coordination number. The coordination number is basically the number of covalent bonds or dative covalent bonds formed with the central metal ion. In this case, the coordination number is the number of dative covalent bonds with the central metal ion. We have to count that, so it's 1 2 3 4 5 6. So the coordination number of copper over here is 6. So it's the number of dative covalent bonds bonded to the central atom or ion. And the shape of the complex depends on the coordination number, so we'll have to learn about that as well. We only learn about 3 different coordination numbers in our syllabus, 6, 4 and 2. If the coordination number is 6, the shape is octahedral. If the coordination number is 4, the shape is tetrahedral. And if the coordination number is 2, it's linear. We find this using the valence shell electron pair repulsion theory, which we have learnt in AS. So an octahedral shape would be that of CuH2O6, the compound we drew just a while back. It would have a shape like this. So this is like a square planar. And with a square planar, you'll have one H2 on the top and one at the bottom. So this is an octahedral shape. Complex with a coordination number of 4 would be CuCl4 2 minus. This will have a shape like this. So Cl over here, a Cl over here, one at the front and one at the back. This would basically be in the shape of a tripod. and it will have a charge of 2 minus. This has a charge as well. This has a charge of 2 plus. This is a tetrahedral. It might be square planar as well. The only two we learned directly are cisplatin and transplatin. And we'll also learn about a linear example. An example of a linear shape with coordination number 2 will be CuCl2 minus. So this will have a shape of CuCl in a straight line and a charge of -1. So this is a linear shape. The next topic we'll move on to is the naming of complexes. It depends on the ligand. So some common ligands will encounter are water, OH minus, NH3, Cl minus, Cn minus, CO, and we have a name for each of them. So if we have water in a complex, we call it aqua. For OH minus, we call it hydroxo. For NH3, we call it amine. Cl minus is chloro. Cn minus is cyano. And CO is carbonyl. It's a carbonyl functional group. We can have some examples. So this we'll use the same example again of CuH2O6. We can also call this the type of ligand. I'll not call it name because the name might be confused with the name of the complex. So for this we have 6 water. The prefix for 6 is hexa. So we have 6 water. So hexa aqua. Now now for the remaining part, we have to describe the copper. We'll have to find the oxidation number of copper. In this case, the oxidation number of copper is +2. So this is hexa aqua copper 2. Since this is an ion, we'll write it's a hexa aqua copper 2 ion. An example of the presence of a OH minus ligand would be in ZnOH4 2 minus. Here we have 4 hydroxo group. The prefix for 4 is tetra. So we have tetrahydroxo zinc cation. In this place we don't write zinc ion since this has a minus charge. Since this ion is negative, we'll end it with ATE. If we had a copper ion which was negative, for example CuCl4 minus, we'll come into that soon. So CuCl4 2 minus, this would be tetrachloro since we have 4 chlorine or 4 chloro groups. So tetrachloro cuprate 2 ion. So tetrachlorocuprate 2 ion. We don't call it copper 2 since that is used if our complex is positively charged Now for zinc, we don't have to write the oxidation number since zinc is not a transition metal. We do it only for transition metal. So this will be a zinc ion. And for ammonia, an example will be Cu NH3 2 plus. This would be tetra amine. When we are writing the name of the complex, for amine we have to use double M. This is a bit different. This is copper 2 ion. For Cn minus, we can have iron and then Cn6. This is 4 minus. So we have 6 cyano groups, so hexacyano. Now for iron, for the negatively charged complex, the name is not ironate. We use the Latin name, which is ferrate. So you have to remember the names of the metal we use when we have a negatively charged complex. So for copper it's cuprate, for iron it's ferrate, for zinc it's zincate. These are all the ones you need to remember. In this case the oxidation number of iron is 2, so this is hexacyanoferrate 2 ion. And for a carbonyl group, an example will be NiCO4. This has a charge of 0. So when we have a charge of 0, we don't have to mention the oxidation number or the fact that it's an ion. We can simply write it's a tetracarbonyl nickel. Now a property of transition metals were that they form colored compounds and ions, and in solid form they are colored more often than usual. We have to find the reason for this. So transition metal complexes are colored because they have a non-degenerate d subshell. So initially all the d orbitals, so there are 5 d orbitals, they all are at the same energy level. So when they are all on the same energy level, this is called degenerate d's. So they are called degenerate d orbitals. They are all on the same energy level. Now when they are in a complex, the d orbital splits, so some of it becomes higher energy orbitals while other become a lower energy orbital. This creates a gap between them. So there is a gap between them over here. And if you studied physics, we have a case of spectra over here. If you didn't, basically when frequencies of light come and hit this atom, when different frequencies of light come and hit, the electron on this level can absorb that energy and move to the higher level if the energy or the frequency is exactly equal to this gap. So if the energy of the light is equal to this gap del E, the electrons from the lower level jumps up to the higher level. So the light gets absorbed. Only lights with energy equal to del E gets absorbed. So only certain frequencies of light get absorbed, and if that happens, the atom appears to, or the element appears, not the element, the complex ion appears to have the complementary color of the absorbed color. So in an isolated metal atom, the d orbitals are degenerate, and if it's in a complex ion, the d orbitals differ in energy, so there is an energy gap between them, and this is due to the overlapping of the ligands with the d orbitals. Now when light falls on it, due to the energy gap, specific frequencies of light are absorbed, and if that is in the visible range, the ions appear to be colored. Now if the ligand is stronger, the energy gap becomes larger, so the color changes. And remember the fact that a strong ligand splits the d orbital, more than a weaker ligand. An example of this would be CuH2O6 again. This is blue in color, so CuH2O6 2 plus is blue in color, and if I react it with ammonia, we'll get 4 moles of ammonia, we'll get CuNH3 4H2O6, sorry, H2O2 2 plus 4H2O. The color of this compound is violet blue. Ammonia is a stronger ligand than water, so there is a change in color. In this case, orange light was being absorbed. The complementary color of orange is blue, so the compound appears blue. And for CuNH3,4, yellow is being absorbed, causing it to appear violet blue. Now for the complementary colors, you have a color wheel. So this is the color wheel. So if it absorbs orange light, it appears to be blue. If it observes yellow light, it appears to be purple. So how you use this table is basically look at what color it absorbs. So in case if it absorbs red, the color will be the opposite to it. So if it absorbs red, the color will appear to be green, and vice versa. If it absorbs green, it will appear to be red. If it absorbs purple, it will appear to be yellow. If it absorbs blue, it will appear to be orange. This is a better representation. If the energy gap increases, the light absorbed goes from red and moves clockwise. So initially it was absorbing orange, so from orange it moves clockwise and goes to yellow. So the absorbed light goes from orange to yellow, which causes the light that the color we see to go from blue to purple. Now other factors that affect the color of a transition metal complex are the coordination number and the oxidation number of the transition metal. So the effect of oxidation number. The oxidation number affects the color because if the oxidation number is higher, the charge density will be greater because the ion is more positive. So in chromium 6 plus has a high charge density since it has a high oxidation number. This will cause the splitting to be greater, so the color absorbed goes from red to orange to yellow, depending from where it starts, but it will change. So an ion with a high charge density will attract the ligand more strongly, and hence the color will change. The other effect will be due to the change in coordination number. For the second point, or the effect of coordination number, we don't have to remember the details or understand why it happens, but we have to know that the splitting of d orbitals differ with the change in coordination number, and that's the reason behind the color changing due to the change in coordination number. An example of this would be CuH2O 6. This is blue 2 plus, whereas CuCl4 2 minus is yellow. We are changing the ligand, but we are also changing the coordination number here, and that also affects the change in the color. That's it for this video. In the next video, we'll be learning about the transition metals individually and their reactions with hydroxides and amines, and we'll be learning about their colors in different compounds and how they act as catalysts. That's it for today.